We are in section 6.4, Arithmetic in Different Bases. So again, what we're going to do is we're going to focus on just running through some examples. So I'm going to try to do one of each type. And then from there, what we're going to do is just kind of talk about the general form of what to do with these pieces. So when we try to add in different bases, the big idea is you want to look at how addition works in that numeral system. So, for example, 0 plus 0 would still be 0 if we're working in base 2 here. 0 plus 1 is still 1. 0 plus 1 is still 1, but 1 plus 1 is 2, but when we convert 2 to binary, we get 1, 0. Because we have 1, 2, and 0, 1s. So that's why it looks like 10 instead, so it's a little bit different. So we're going to try to find the sum in binary of 1, 1, 1, 1, 0, and 1, 0, 1. So first thing I'm going to do is I'm going to set them up just like we would with normal addition. But remember, everything we're doing here is in binary. It's not in our regular numbers, okay? So 0 plus 1 is 1, because we can always look at our chart. 1 plus 0 is 1. 1 plus 1 would be 2, so that's really 0, 1. 1 plus 1 is really 2, so that would be 0, 1. 1 plus 1 is 2, so that would be 0, 1. So then we get this value, 1, 0, 0, 0, 1, 1, base 2. Now another way to handle this would be to convert both of these numbers to decimal numbers, do the decimal and decimal, and then convert it back to base 2. So decimal is base 10. So that would be another option. I'm going to leave you to do this in a hexadecimal on your own, because the next example we're going to look at is going to be in hexadecimal. Subtraction in binary is going to work in a very similar way, but it's still going to be a little bit confusing. So what we're going to focus on is subtracting in hexadecimal. So we have 1e from 5. Okay, so we're going to do 1e, because that's the bigger one, and we're going to subtract 5. Now remember, e in hexadecimal was 14. So e in base 16 was 14 in base 10. Okay, so 14 minus 5 would give us 9, and then 1 minus 0 would give us 1. So again, this would be our hexadecimal number, or base 16. And again, if we wanted to check it, we could convert both of these to our decimal equivalents, subtract, and then convert that number that's in base 10 back to hexadecimal. So now that we've looked at addition and subtraction, next we're going to look at multiplication. So we're going to do an example of multiplication in both base 2 and base 16. So the first one we're going to look at is in base 2. So we're going to start by making a chart just like we did before, so we know what we're looking at. So again, these are going to work the same way. We just have to convert them so that they're all in base 2 instead of base 10. 0 times 0 is 0. That wouldn't be any different. 1 times 0 is 0. Again, no different. 1 times 0 is 0, and then 1 times 1 is 1. That's all we need. So doing multiplication here is very nice. Now what I'm going to do is, because we have a 1, 2, 3, 4, 5-bit number times a 3-bit number, I'm going to do each layer, because we're going to have 3 layers, in a different color. So first we go through 1 times our 5-bit number. So 1 times 0 is 0. 1 times 1 is 1. 1 times 1 is 1. 1 times 1 is 1. And 1 times 1 is 1. So there's our first layer. Now our second layer, we want to leave a space, so you can put an X there, because we want to make sure that these line up, because just like in long multiplication, we're going to need to add it all together once we do all the layers. So now we have 0 times all of this. 0 times 0 is 0. 0 times 1, 0. 0 times 1 is 0. 0 times 1 is 0. And 0 times 1 is 0. So I know that seems silly, but if it was not 0 and it was something else, we'd want to have that step. Now we're going to do our last one. So we're going to multiply 1 by our 5-bit number again. So this time we have 2 placeholder x's, and then we go through 1 times 0 gives us 0. 1 times 1 gives us 1. 1 times 1 gives us 1. 1 times 1 gives us 1. And 1 times 1 gives us 1. So we get our number again with two placeholder zeros. Now we're going to add all of that together. 0 plus nothing is 0. 1 plus all this would be 1. 1 plus 0 is 1. 1 plus 0 plus 1 would be 2. Base 2 would be 10. So we carry. 1 plus 0 plus 1 plus a 1 would be 3, so that would be 11 in binary. 1 plus 1 is 0, 1 in binary, and then 1 plus 1 would be 0, 1. So our answer would be 1, 0, 0, 1, 0, 1, 1, 0, base 2. So it's a little bit different, and I know it does get hard to keep track of everything with all the zeros and the carrying. So again, here it's helpful to have that addition chart out as well. You can confirm your results by converting the numbers to base 10, multiplying in base 10, so it would be your normal arithmetic, and then converting it back to base 2, and then writing all the entries in a multiplication table for your base, for a bigger base, such as base 16 can be very time consuming, so you may prefer to multiply in base 10 and then convert the answer back to your given base. Okay. Or what you can do, and what I've taken the liberty to do, is I did the 5 table for every in 16. And I already multiplied those out. So we're going to go ahead and jump to multiplying in base 16. Okay. E times 5, we just go up here, was 46. So we get a 6, carry the 4. 5 times 1 was 5, and then we add 4, so we get 9. So our answer is 96, base 16. Now just to show you how this would work if we convert it and then convert it back. 1e would be 1 times 16 to the first plus e times 16 to the 0. So that would be 16 plus 14, so 30. 5 would just be 5, because it would be 5 times 16 to the 0, which is just 5. So if we multiply 30 by 5 in decimal, we get 150. And again, this is base 10. So if we want to convert 150 back to base 16, we would take our 150, take out a 16. When we do that, we get 9 with a remainder of 6. So again, it'd be 96 base 16. So we get the same answer. I just wanted to work that out for you just to show you how you can work it two different ways. Now division kind of works the same way. For division, you need a giant table like this, so you know like how big you can go. You guys can read that one on your own. I'm not going to make you do any problems with division, but again, it depends on your vocation and what you're going into, whether that would be useful to know.